Hello and welcome to today's video. We're going to talk about proofs with truth tables. So in the last few videos we've kind of done some truth tables, we've done some difficult truth tables with implications, but we still haven't really talked about why you would want to do these. And the reason why you'd want to do them is for proofs. So formulas P and Q are logically equivalent if and only if the truth conditions of P are the same as Q in all situations. So basically what we can do is we can create a truth table and we can compare two propositions, two complex propositions even, and if their truth values are always the same, we can say they're logically equivalent, and that's a proof that can allow us to do some more complicated things later on. So again, as usual, we'll do some review. So truth tables are used to show all possible combinations of statements and connectives, and remember, with truth tables we start with the most basic propositions that we need and we work our way out to what we eventually have to compare. So, and also I want to touch on a tautology. That's a logical statement that's always true. So in your truth table, a tautology will occur when you have all truth values. Then lastly, a contradiction, a logical statement that's always false, and that's when your truth table will just be all falses. So this is an example of a proof that you would use a truth table to complete. This says not P or Q implies or is logically equivalent to, that's how I would read that, is logically equivalent to not P and not Q. Okay, so that's what the triple arrows, the triple equal sign means. So now how do I prove this using a truth table? Basically, like we said in the introduction, we need to show that this part has all the same truth values as this part. If that's true, then they are logically equivalent. If it's not true, they're not. So basically I need to treat it as two separate problems. The first one I need to end up with this, and the second one I need to end up with this. And well, you write them as one truth table, but it's really two separate problems, two separate goals. And the building blocks for both of these are P and Q. And then I see that I have not P and I have not Q, so I'm going to include those next, because I want to start with simplest and then move out to most difficult. Okay, and then what do I have next? I see, well, I have P or Q. Then I have not P or Q. Then lastly, I have the not P and not Q. So these are the parts of the truth table. And what I'm going to be comparing are these last two columns, right? I'm going to be comparing this column to this column. And if they have the same truth values, well, then we can say they're logically equivalent. So let's start filling out the truth table. So as usual, we can do all parts, all possibilities for P and Q. As always, there's two possibilities for the true and two possibilities for the false, and that's because the values of the Q could be changing. So the possibilities are true, 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 false, false, true, false, false. Okay, so now not P. Again, not P is obviously just going to take the opposite of the truth value of P, so it's going to be false, false, true, true. Similarly, not Q is going to take the opposite of the truth value of Q, so it's going to be false, true, false, true. And now we get into P or Q. So remember, this is an inclusive or, so P or Q really means P or Q or both. So it can be both P and Q. Okay, the only thing that it can't be is neither one. So P or Q, the first one, both are true, so that's going to be true. The second one, I have a P. The third one, I have a Q. The last one, I have neither one, so that's when P or Q is false. I don't have either one. Then now we have not P or Q. Well, if I don't have P or Q, I'm just going to do the negation of what I just did. So that one's going to be false, 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 true. Again, because when we do negation, all we do is we switch all the truth values. Lastly, we have this final step. So, and what we want it to see, we want to see three falses and then a true. That would prove that they're logically equivalent. But if that's not true, they're not logically equivalent. So this is kind of the moment of truth per se. So not P and not Q. Is that true here? So not P and not Q, well, they're both false, so that's false. So not P and not Q here, well, one is true, one is false, that's false again. Not P and not Q, one is false again. And then lastly, both are true, so that means not P is true and not Q is true, so that means that's true. So notice these are equivalent. So this is equivalent to this, and that means the statements are equivalent. So that means not P and Q is equivalent to not P and not Q. So it was not P or Q. It's equivalent to that. This is one of De Morgan's laws, and the second one is actually the next De Morgan's law. So we're going to prove that. So what we really just proved is this is an important law in just math in general, and especially in set theory. So what you can do is you can kind of distribute that not symbol. So remember, we kind of had that go in there and then there. But when you do that, you switch the sign in the middle. So it was or, and then it's going to become and. That's something that we'll get into much deeper later on. But this is the proof behind it. This is how you prove that De Morgan's law. All right, so next one. You'll notice that this is the exact same rule. So if you knew that rule, if you knew that you could, okay, well, I can distribute the negation, then switch the signs, you would know that this would be true. But this is something that we do want to prove. This is something that teachers often will put on tests because it's an important law, but it's good to know the proof behind it. So then I have, okay, well, what do I have? What are my components of this one? Again, not P. Again, I have not Q. Remember, I start from the smallest and get to the most difficult. And now this time I have P and Q. And then I have not P and Q. Then lastly, I have not P or not Q. So similar to our last one, but not the exact same. Okay, so I'm going to go pretty quickly through this one. Again, our 4 possibilities: true, true, false, false. Then our 4 possibilities for Q: true, false, true, false. Not P is just opposite truth values as P. So it's going to be false, false, true, true. Not Q, opposite truth values as Q. So false, true, false, true. And now P and Q. P and Q is obviously only going to be true in the situation that both P and Q are true. So that's going to be the first one's true, and then the rest are all going to be false. Okay, now I'm simply taking the negation of not P and Q. So now it's going to be false, true, 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 because all I'm doing is doing the opposite of what it was. Then now I have not P or not Q. So now I'm looking for, okay, so not P or not Q is only false when I have both P and not Q, right? So not P or not Q, as long as one of them is true, I'm good. But the first one, both of them are false, so that's going to be false. The second one, not P is true, so the whole thing's true. The third one, not Q is true, whole thing's true. The last one, both are true, whole thing's true. So these two, I notice, are equivalent again, so that equals that. So we have the evidence to say that not P and Q is logically equivalent to not P or not Q. And if you notice again, it was the same kind of reasoning with distributing that negation sign as the last one, and these two rules are called De Morgan's laws. Really important mathematical rules. Hopefully you kind of understand how we do those proofs now. Now let's look at the last one. So this is kind of a different type of proof, but you use the truth tables the exact same way. So now you're determining if something is a tautology. So what you need to do is you're basically trying to figure out, okay, is this true in all situations? So no matter what P and Q are, is this going to be true? You could just plug in Q's and P's, but that would be really confusing. The standard way to do this is to do a truth table and then check, well, is it always true? So we want to have this on the last column, and then we're looking for, is it a straight line of truths? So again, as always, we start with our basic parts. We've got P, we've got Q. What else do we do? Have not P, and we have not Q again. So those are our basic parts. Then now what do we have? We have P and Q. We have not P or not Q. Then lastly, we have what we're actually trying to prove. We have P and Q, or not P or not Q. And what we're looking for is we're trying to prove it's a tautology, so we want to see if that last column is true no matter what. And let's think about the first second about what this is saying. So this is saying P and Q. Okay, so that means P and Q are true, or not P or not Q is a tautology. So is this always going to be happening? So basically what it's saying is is P and Q true, so are both true, or is one always going to be false? And well, that's my thinking. My thinking is that this is going to be true because this part implies at least one is false. That's how I would read that. At least one is false because it's not P or not Q, or both because it's inclusive or. And then this one I would read as both are true. So both are true or at least one is false. That means, to me, that means, oh, well, that's probably going to include all possible scenarios. I don't see a scenario where that wouldn't be true. So I think it's going to be a tautology, but that's just intuition. We don't want to rely on that for the problem. So again, our 4 situations should we have it now? True, true, false, false, true, false, true, false. Not P, opposite truth values as P. Not Q, opposite truth values as Q. So false, true, false, true. P and Q only is true if both of them are true, if P and Q are true. So the first one is true, the rest it's going to be false because at least one's always false for the others. And then now we have not P or not Q. Okay, so at least if one of not P or not Q is true, then we're good. First one I notice is false, right, because both are not true, but the rest have at least one of not P or not Q true. So we're looking at these columns here. And I see in the last 3 rows, at least one of them is always true. The first one, both are false, so that statement's going to be false. Okay, so now the implication, well, not the implication actually, just the statement, says P and Q or not P or not Q. So now I'm looking at these 2 columns, and I'm seeing is one of them always true, basically, because it's the inclusive or, and if both are true, that's fine too. So I need to figure out, is one always true? Well, yeah, the first one's true, 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 true. So it seems like this is in all situations, this is going to be true. So that is a tautology. So because all these are true, tautology. So the answer is yes. So yes, it is 1 because in all situations, no matter what P and Q are, this statement is going to be true. And it makes sense for that logic that we were kind of talking about earlier. And I recommend you do that when you see a proof. Just kind of understand what you're actually proving instead of just jumping into the math behind it. So hopefully now you kind of understand what truth tables are actually used for. And if you have any questions, don't hesitate to contact me. Have a good one.